Okay, welcome to the third in this series of lectures on computing. This one is called The Processing of Computing and is actually part one. Okay, it is the first part of two parts in total. And what we're doing here is we are looking at 5 key areas. We're actually looking inside the box as such. We're going to distinguish, as I say, between peripherals and the internal components, and we're going to cover each and every one of those points. Let's begin. I want to introduce you to the 3-box model. The 3-box model was introduced or proposed in 1945 by a gentleman called John von Neumann. He proposed a computer system that would be constructed of a processor. This would be the part that would do the work of the system. This is often incorrectly termed the brains of the computer. As my class will tell you, I loathe that term. There's no correlation between the brain and the processor. This is not the platform to discuss that. However, the processor is the idea that that's the bit that does all the work. Remember, this is a theoretical concept of computing. It is the processor that does the work of the computer. There is main memory. Main memory is the simplest of all of the parts. It's simply there to store the instructions and data of the computer. The third and final component is the I/O, or input-output. This allows this computer to communicate with the outside world, with devices outside of itself. All 3 components are tied together by the system bus. The system bus, or external bus, connects all 3 together, and they allow a single binary word to be transmitted between all 3. Whilst it should allow the processor to communicate with the other 2 via an address bus, so it should be able to address the other 2. What we're going to have a look at is we're going to be looking at those parts in much closer detail. That's called the 3-box model. It's a proposal by von Neumann. So let's have a look at the first part, this central hard-working part of the system. The processor, this is where the work is done. This is where your computer programs are actually being created or executed. Each and every instruction that your computer processes goes through a processor. Now, I did say a processor rather than the processor. That's because in modern day computers we can have more than one processor. For example, you could have a quad-core processor that actually has 4 processors inside of itself. Equally, we may have a GPU, or graphical processing unit. This is a chip which has been developed, a processor that has been developed to handle graphics. The problem for the general purpose processor is to handle graphics requires a lot of instructions and code. These ones, the GPU has been developed to specifically handle the demand of graphics. Modern graphical processing units are actually designed to deal with 3-dimensional drawings and imagery. Though it is possible for the processor to do so, it's much more effective to allow the GPU to stay that on. So when your computer receives commands to do with visual effects, nowadays it's your GPU. It's still a processor, but it is a dedicated processor rather than a general purpose one. Okay. Most people will use the term CPU and processor. By the way, CPU, Central Processing Unit. Most people will term that as synonymous with a processor, and that's fine for everyday use. But from the computing point of view, that's not correct. This is a processor. There is the processor. This whole model is the CPU. The CPU comprises of, at its most basic, a processor, main memory, and system bus. The input-outputs are not input-output devices, but a means by which the CPU can communicate with the outside world. So if you have a processor that is dedicated not to communicate outside of itself, then the CPU will be the processor, main memory and buses. But since we want our processors to share information and get information from elsewhere, we have an input-output system. These are not the devices themselves, but a means by which the CPU can communicate outside. And the object outside of the CPU are called peripherals. The important thing to remember there is that the processor is part of the CPU. It's part of the von Neumann model. It is not the CPU in itself. Next part is the main memory. There are three parts of main memory that we've really got to worry about. There's RAM, random access memory, read-only memory or ROM, and electrically erasable programmable read-only memory or EEPROM. You may even see it referred to as E²PROM, but most commonly it's known EEPROM. All three of those, in some context or other, exist within your computer system. Some of them are disappearing, some of them have been updated, but all three will exist in some form or other. Let's have a look at the first one, random access memory. There's an example of random access memory. When you run a program in your computer, the instructions and the data will be loaded into RAM. It's loaded into this memory, and this is the main memory that is mentioned as part of the three-box model. It's your RAM that forms part of the CPU. So your instructions are loaded into this type of memory. And there are, in fact, just as there are three types of memory, there are three types of RAM. There's DRAM. DRAM is short for Dynamic Random Access Memory, or Dynamic RAM. Dynamic RAM is the simplest form of data of RAM. So memory is the simplest form of the in the model, and dynamic RAM is the simplest of the simplest. It's very simple to construct and it just holds on to data, but there is a problem with it. It leaks. As it holds electricity, it releases some of that electricity. It can't hold on to it. It's a little bit incontinent, if you will. And so it needs refreshing. It needs to be, all the data in it has to be refreshed, roughly about 64 milliseconds. Every 64 milliseconds, you have to refresh it. That means your computer, every 64 milliseconds, is busy refreshing all of your RAM. So the more things you've got running, the more it's got to refresh. And so the slower your machine can be. It's actually not dynamic RAM as such that you have inside your computer, but it's very close relative, which is SDRAM. The S is short for synchronous. The only difference between these two, it still leaks. It's still unreliable as such, but it's very, very simple. The synchronous part means that the memory locks in to the same clock speed as the buses, as the control bus, the system bus. So your memory, when it plugs in, is running at the same speed. The alternative with a standard dynamic RAM is to have something called asynchronous. That's just sticking the A in front of the word synchronous. And it means that the memory runs at its own rate. So it can actually take the data and have it ready for the control bus or the system bus to collect it. But your computer, for simplicity's sake, it means that your memory doesn't need a clock, so therefore it can just sit there and it just takes the clock speed that your control bus is running on. So synchronous dynamic RAM still leaks. SRAM, you'd have thought synchronous RAM, but actually it means static RAM. This does not require refreshing, and obviously that kind of came from from the other two statements. This locks onto it, so therefore it does not need refreshing, so it's much faster. The whole way it's developed is. But it is expensive. It takes up more space because it's got more components on it. So to get the same quantity of memory, you've got to have a bigger device, which means you've got to pay more money, which means SRAM is expensive. You do have some SRAM, there may be some on the side of your chip, on the side of your processor. Your processor will have some SRAM to make things really as fast as possible. But at the end of the day, most of the RAM you've got is going to be SD-RAM. SD-RAM you may see labelled as DDR or DDR2 or DDR and so on and so forth. DDR means double data rate. So if you want to add to the SD-RAM, you could add the letters DDR to the front of it, so you've got DDR SD-RAM, which is double data rate synchronous dynamic RAM. That's something to throw around in parties. Just to mention volatility. Volcanoes are volatile. Okay? That doesn't mean if you take a volcano to the pub, it's going to get upset with you very easily. But they get volatile. That means it kind of unpredictable. Your memory is not unpredictable. In terms of IT, we talk about volatility in the sense that all RAM is volatile. When you pull the power out of your computer, the data that is stored inside that computer, in that RAM, is lost. RAM cannot hold on to the data it has without power. As soon as you withdraw power, you lose the data that's stored in RAM. It is volatile. If you wish to store data long term, then you need to use something else, long-term storage. So another term for RAM, by the way, is short-term memory. Because long-term memory is your hard drives, your CDs, your memory sticks. But those add other dimensions. So when we talk about volatility, we're talking about two types, volatility and non-volatility or non-volatile. RAM is volatile. The other type of memory is ROM. ROM is short for read-only memory. This type of memory is the instructions and data that it holds are sent to it during production. So when that chip is being produced, they will burn the data into that ROM and it will remain in there. You cannot then overwrite it. You cannot then change it. So the idea behind this is if you've got some settings inside your computer that you want fixed, the manufacturer wants this stuff is always true, then you burn it onto ROM and it stays inside your computer. ROM is used throughout your computer, and it used to be true that ROM used to exist in the form of BIOS. If you know of your BIOS, when you switch your computer on and you see the text come up, that used to be loaded into ROM. That's not true anymore. We use another type of memory for this, which is called flash memory. And that's because flash memory does allow us to reprogram the system. So let's have a look at the earlier version of that. EEPROM, electrically erasable, programmable, read-only memory. It's at these points you realise why we use these TLAs, these three-letter acronyms, because they constantly talk about electrically erasable, programmable, read-only. It's exhausting. EEPROMs are different in the sense that we can actually use electrical current to remove the data in there and rewrite to them. EEPROMs have been around a very long time. These particular systems are used, as I say, they are used in your computer, but less so now, and for several reasons. One of the primary reasons is that if you wish to rewrite to this device, you have to rewrite the whole thing. So if there's one small part of it that is incorrect or you want to change, you actually have to change everything in there. And that takes time. Reading from an EEPROM is fine, but if you wish to write to an EEPROM, it's 100 times slower. So an EEPROM is fine to read from, but to write to is much slower to do so. So I moved on to the long sheet, my eyes went blurry there. Let's say the benefit of those is to overwrite them, but let's say you have to overwrite the whole thing. So we want an alternative. And it was believed at one stage that the EEPROM was as good as you're going to get, and then they found a new way of doing that. And that was to introduce flash memory. Flash memory, your memory sticks, these wonderful things, they use EEPROMs. The data remains on these are not volatile. They are stored on there. But the difference with the flash memory is that they broke the memory into small blocks. So when you write data to flash memory, it only overwrites a small block of data rather than the whole memory. It's still not as direct as RAM, and it's slower, but it's much, much faster than using a standard EEPROM. There is a problem with these. The problem with them is that actually the very nature of the way they work creates a flaw in the way it holds electricity. And it means that they deteriorate quickly. A memory stick, a flash memory, has a very short life expectancy. It is meant to, the estimated average life expectancy is 1,500 connections, or 10,000 writes to the system. It's the writing that damages them. After 1,500 independent connections, or 10,000 writes, it's difficult for the chip to distinguish between a 0 and 1. The component is breaking down, it becomes unreliable. Some of you may have had notices from your memory stick saying, I'm finding errors on here, do you want me to scan it? That could be because it's beginning to find it can't distinguish between the zeros and ones. That is also a reason why you should never defragment or format one of these, because in doing so, you shorten its life. There is an argument out there that defrag doesn't actually improve it at all. Formatting certainly doesn't. But we certainly can tell you that whatever benefits you get from defragging it are lost by how much life you've just removed from your device. Not for long-term storage. Okay, buses. That's a bus. Where's that? I quite like that one. But I like that one as well. I could keep going. Anyway, that's a bus. As we said, in the 3-box model, we had a system bus. So if we start to look at the 3-box model again, I mentioned to you that in the 3-box model by von Neumann, he suggested that there is a system bus that combines all this, and it allows the addresses to pass from the processor to the 2 devices and data to flow between all 3. That, by the way, is a system bus, and if you're wondering which part, it's these wires that are running here. Because in reality, your system bus is actually made up of 3 buses. Those 3 buses are 3 sets of parallel lines. Particularly the data bus and address bus run in parallel lines. The number of lines are dependent upon the unit. You can have 8, 16. Very common now is 32 or 64. The only thing that limits the number of parallel lines we can have is how big your motherboard wants to be. If we can pack in more, we'll take it to 128. Later on we'll have a look, and the next one we'll have a look at the impact of adding more wires to the data bus, the address bus, and the rest of the system. The control bus is different from the other 2. The data bus is bidirectional. It consists, as I say, of 16, 32, 64 wires, and it carries the instructions and the data between the 3 components of the system. The address bus is the only unidirectional. That means the data can only flow in one direction. It is the only unidirectional bus in the whole system. It travels only from the processor across to the other two devices. And it carries the address that the processor is referring to. The control bus has a number of settings in there to tell the processor or the other components what is going on. So the first thing your processor will do if it wants to communicate with something is it will send the address down the address bus. That will reach the component that it wants to talk to, and the next function will be the processor using the control bus to notify that component what it wants it to do. Do I want to read data from you? Do I want to receive data? Or do I want to send data to you? But equally, the device can tell the processor certain things. So the control bus is bidirectional. For example, maybe your processor is talking to your graphics card, or it can't talk to the graphics card directly, but it talks to it through the port, and it says, I want to send you data. But your graphics card is busy, so one of the lines that runs down there is the busy flag. So the device will simply say, I'm busy, sorry. Another one on there is the reset register, the reset control. And that actually does do a hard reset of the device. It basically tells it to get back to where it was before. So if your computer locks up, Control Log Delete will send a reset down the control bus wire. Okay. We can have lots of things connected to our processor. We can have a hard drive, we can have a printer, we can have the monitor. Except as I said before, you actually can't connect any of those directly to the processor. What is important to recognize is that no matter which one of those devices you go to, as long as it's not main memory, your processor cannot be talked to directly. So I shouldn't say talked to, communicated with. Data cannot flow between these and the processor. What you require instead is some form of controller. So that I/O device in the von Neumann model is called an I/O controller, or input-output controller. Some controllers are bidirectional. For example, I can read and write data to my printer. I can read and write data to my hard disk drive. I can send data to my printer, but equally my printer may wish to inform me of other things. It's out of paper. It's out of ink. It's Friday. Doesn't always tell me that one, but yeah, could do. So your printer is also using a USB port, which can be bidirectional. Your monitor is unidirectional. You can only send data to your video, to your monitor. An alternative to that in the other direction is obviously your keyboard. Your keyboard allows data to flow only inwards. So you must have a controller that allows you to communicate with the processor. There is no way that these devices can communicate directly with your processor. These are on the periphery. These are on the perimeter of your computer. The perimeter fence, if you will, is the controller. Since these are not able to directly communicate with the controller, they have to connect to these devices through these controllers. They are termed peripherals. So any device outside the 3-box model is a peripheral, regardless of the fact if it's inside your computer or outside. The I/O controller, you might notice that I put USB port, but I put controller in this. That's because of this part here. I wanted to highlight the fact that the controller actually consists of 3 parts itself. The controller has 2 parts, which is the interface. The interface is a set of electronic components that allows that controller to communicate with the system bus. Another set of electronics sits on the other side of the controller, and that allows the peripheral to communicate with the I/O controller. The central part, the registers, is where the data can flow between the two devices. It is in the data registers, so it's in the registers that any control commands are sent, any data is sent. Okay. Let's have another look at one of those peripherals, which is secondary backup or secondary storage. We're not going to have a look at too much of this. We don't have to go into huge detail with hard drives or anything else, but there is a list of certain things you need to be aware of. We have a variety of storage devices available to us, still in existence and still very popular hard disk drives. They're not disappearing yet, but they will begin to. You are of the generation which will see the demise of the hard drive. But why will you see the demise of the hard drive? Because flash memory is beginning to take over. Hard drives, however, have a much longer life expectancy, so there is a balance there. Hard drives use magnetism, north, south, to represent the zeros and ones. The head will magnetize a block on the metallic surface, and that will signify if it's a 0 or a 1 in that point. The hard disk drive is considered non-removable. Now obviously nowadays you can actually have removable hard drives, but if any of you have ever taken one out and dropped it on the floor, you'll know it's not exactly designed to be thrown around. I've had 2 of these and both of those have been dropped and stopped working. I've had hundreds of these and I throw them around all the bleeding time. CDs, DVDs, all of these, Blu-rays are optical. That means they use light. They use light to see, just like we saw in the ticker tape and everything else in the previous lecture. We are talking here about using light to read the data off these disks. It's only the method by which the data is stored and the way we read it that has changed, but the fact is we're still using light to read data. Worth noting that the only difference between a CD-ROM and DVD-ROM, those two, and Blu-ray, is that those two use red lasers and Blu-ray uses blue, and it's a much, much tighter beam. Because it's much tighter, because blue has the narrowest waveform, it actually means you can compact more data onto the disk. And we've seen flash memory, it's an electronic storage. Oh, pictures. Just in case. I should have been clicking through that, just going, ah. Good. Addressable memory. So we've agreed that, we understand that in the von Neumann model we need memory, and the one question is how do we address that memory and how does it actually work? Well, let's have a look at this analogy for it. Here we have a set of 10 memory blocks, each with a unique address. They're of a certain length, they don't have to be 1 digit, so they can be 8 bits or however long we want them to be. But what I can do is address them, and each one of these blocks is containing something different. Imagine that these are lockers at your school. Each locker can contain a different item, and if you wish to, all you've got to know is the address of the locker you want. Go to there and you can take the data out of that. Your processor will send the address to the locker it wishes to take, and it will simply then take the data out of that box. It won't destroy the data that's in there. But if you write anything to that location, then you instantly destroy what is already there. So, as we can see there, we have a series of numbers, we have a boolean, we have strings. This one's not even being used yet. So we can have different states within those memory blocks that we can refer to. And that's exactly what your computer does. Your computer uses main memory and segregates it up. So if we're looking at your browser, we can actually glance at how the memory is working, and we can find out how the data is stored in there. And within a range of data, we can actually see what's being stored in that location. Your computer can make a call to that area. Notice how your operating system is held in main memory. Notice your temporary files running to help your computer run that little bit faster. Your game is running in the bottom here. All of this is being run in segments of memory. Each one has a unique address which your processor can refer to and either send data to or receive data from. This idea of addressable memory came from, again, two other people, or in fact one we've already met and another one we know of. But the stored program concept is exactly what was written down there. The idea is that we store a program in main memory, we then fetch the instructions from that main memory, execute them, and decode and execute them one at a time. So we take each instruction, execute it, and perform it. This concept was actually arrived at by two people, von Neumann and by Alan Turing in 1945, independently of each other. They both proposed the stored program concept, and it is the same process your computer uses now. The idea is that your main memory holds all of the instructions and data, and that is transferred to the processor, fetched by the processor, executed by the processor. Each instruction has a unique identifier, a unique code, a unique address, and that is how it's being collected. So I'll look at an example of how that works. This could be a single bit of data in one memory location. As far as the stored program concept is concerned, that in the memory can either be the denary value 70, the hexadecimal value 46, the letter F, or add these two numbers together. It is up to your computer, up to your processor to decide what to do, dependent upon where that instruction is in the sequence that it's going through. If it's just received it first time, it will be an instruction. If the next thing, it may be a value, depending upon the instruction it received. Your processor will know which one it is. But from a memory point of view, it's exactly the same binary digit. It can represent any of those factors. That means just main memory address. So that's what we call an address when we're referring to it as main memory address, MMA. So if you see main memory addressing, it simply means a unique address that we use for that location. Now I've been using the term von Neumann architecture, and I've been using it quite loosely. Von Neumann came up with a three-box model. He also came up with a proposal for the von Neumann architecture. This is the proposal that von Neumann came up with. It's the proposal that meets our modern-day computers. Our modern-day computers use the von Neumann architecture. And when I say our modern-day computers, I mean our desktops. The computer you use probably at home, sitting on the desk at home, is using von Neumann architecture. The idea here is that we have a processor and we have our main memory, and that's our CPU. We're ignoring the I/O part, and here's two of our buses. We can see the address bus is unidirectional. It sends data from the processor to the main memory. Inside our main memory is either data or instructions. It is up to the processor to decide which is which. The data or instruction will then flow up and down the data bus. That means that your instructions and your data are fighting for resources at the same time. It means it's actually a slightly slow system, because you have a conflict of interest. Where the instruction calls upon a value, it's then got to wait for an instruction to clear or anything else in there. It's a good system, it's a basic system, but there is an alternative. and that's it. The Harvard architecture separates out instructions from data. It still has an address bus, but it actually has two address buses. It has a data address and an instruction address. The processor knows if it needs an instruction or the data. It can actually call data at the same time as the instruction, so it's much faster at executing. They have two separate buses, one for data and one for instruction. Obviously the instruction one at this point becomes known as the instruction bus. But it's still a data bus in all intents and purposes. It's still a set of wires. The Harvard architecture is much faster. But as you probably can predict, it's a hell of a lot more expensive and it's certainly more complex. You need to have a bigger motherboard to cope with this space, or you need some other methodology by which you can actually get this to work. Luckily for us, we have that. Microcontrollers are basically a computer in a chip. Inside this chip is processor, main memory, input-output ports. Everything to allow it to communicate with the outside world. This is a single chip that executes all the commands. The most common form of microcontroller is the ARM processor. The ARM is the processor of choice for most smartphones, most modern day smart televisions, set-top boxes, tablets. It uses something called RISC technology, which means it has a reduced instruction set and it has the computer and the main memory all packed into it. It is so well designed, and due to RISC technology, it reduces the number of transistors. And if you were here for the last lecture, you'll remember the transistor. The average processor has millions of transistors. So your desktop computer has millions of transistors just in that central processor, in your computer. The ARM reduces the number of transistors to 35,000. That reduces heat, that makes it an efficient system to run. Most commonly used as embedded computers. That means an embedded computer is a computer that is set into something, such as an air conditioning unit, such as your phones, such as a microwave. All of these devices use embedded computers, which are nothing more than microcontrollers. They are dedicated. They can perform a small number of tasks. There is no way that an ARM processor can be considered to have all the functionality of a main processor if we reduce the transistors from millions to 35,000. The ARM processor is incredibly powerful, but it's never going to equate to the same thing your processor in your desktop can work at. The difference between this kind of processor is that it can perform small quantities of functions very, very effectively. Your desktop computer can be programmed and reprogrammed to do different tasks, far more complex tasks than this can. Oh, and the ARM uses the Harvard architecture. So your desktop uses von Neumann's, and this uses Harvard to maximize the ability of these machines. Okay, so what we looked at? We looked at the three-box model given to us by von Neumann in 1945, still exists today. It's the principle by which all computers have been developed. We looked at the processor. We had a look at the fact that this is the central part, that this actually executes, performs the instructions. This is where the work is done on your computer. We've seen that the processor is part of the CPU, part of that model. That the CPU is the whole of the von Neumann model, or certainly the processor, main memory and system bus. You have to have that connection. If you are connecting to the outside world, you have an I/O controller. That's the CPU. while the processor is one part of that model. We had a look at RAM. We looked at SRAM, SDRAM, DRAM. We had a look at all those different types. Recognise that your computer is made out of predominantly SDRAM, synchronized dynamic RAM. We looked at the fact that it's volatile, as we can see in the bottom corner. We discussed ROM, the fact that once it's been written to, it can be read from as many times as you like, but it can't be rewritten to. We had a look at the old EEPROM, believed to be fading until some people came up with an ingenious new method, and that becomes a central part of your flash memory. We also noted that the serious flaw in this fantastic piece of technology is that the fact is it's got a short life expectancy. It should not be relied upon. We then explored the system bus. Theoretically, the system bus is simply a connection between the 3 points. In reality, in your PC, you've got a data bus, an address bus, and a control bus. All three use a series of wires. Data buses and address buses are parallel. The number of wires can increase or decrease depending upon your needs, but the address bus is the only one that is unidirectional. We then had a look at the I/O controller, how this is the way you communicate with your processor, that you don't communicate with your processor in any other way, that any device outside of this is considered a peripheral, and that all data passes through the registers part. We had a look at storage. We had a nose around just to have a look at the different types of the way data is stored and if it's removable or not. We had a look at addressable memory. The main thing to remember with addressable memory is that you can refer to one part and you'll get a group of data. It refers to a block, a word, or a byte of data. Didn't move. There it is. We had a look at that example to make sure that we understood that data stored in your memory can be, you can have a look at your memory and you won't be able to work out what that memory is actually for. It's only the processor that can make that decision. We had a look at the two different types of connectivity. We had a look at the fact that von Neumann, the simpler model, the one used inside your PC, and we looked at the Harvard model, much more complex but much more efficient. And finally we looked at the good old ARM, the processor that actually dominates the world, has sold more units than any other processor, powers more items in this world than anything else. Runs a system called RISC. And RISC technology is developed and owned by a small Cambridge company just up the road, one of our largest earners of the country. Very few people know of. And we also understood that the ARM uses Harvard architecture. And that's it. I'm going to do the cartoons now. Hopefully that was useful. Thank you very much. Do let me know either way, one or the other, because it does allow me to change things. Aside from that, we'll watch alongside and we'll do the shell the same as we had a bomb. Bye.
I wasn't hungry for it.
I better turn this off. Last time I left this running all night. But the weird thing was it cut out after, I switched off the lights and it cut out. We don't know why.